Oh, all right, can you hear me okay?
Yeah.
Can you hear me okay? All right.
Yeah, sure.
Thank you for inviting me. So I'm going to talk about foundation models for we are a autonomous driving company that we have a goal to build the world's most trusted driver. And trusted is kind of a load bearing here, and I'll go more into this over the course of my talk. Not just a matter of being safe, it's also a matter of being trusted. And there is a lot of loaded significance to this. And I think it's important for us as technologists to really keep that trust in mind. We are now deployed in San Francisco, in Phoenix, in LA, in Austin. You can take rides in many of those cities as the general public. We are starting in Atlanta. We are about to start in Miami, I believe. We're starting also in Washington DC. So a lot of expansion planned for the next few months. And then in general, we're starting to explore a lot more of the US. In particular, we are going to start doing some data collection and some testing national soon, I hope. So if you're local, hopefully you'll get to see some of our cars roaming the streets first. We have been serving more than 250,000 day trips per week by now. It's a big number. The reason I flash this number is that there is something to scale that really changes it. If you start thinking about the kind of things that you observe and you have to be reactive to at the scale of driving these many miles per week, think of it as one way to think about it is the kind of things that you hopefully never see in your life as a single driver yourself. We probably see them every week. Right? So when you think about driving, when you think about the nominal driving that you're doing in your everyday life, this is a good problem to solve. We think we have a good solution to that problem. This is not the problem that keeps us up right now in terms of the technology development. What really sort of is driving the technology development today is really dealing with the problem of scale and the problem of dealing with the attending problems of things that happen rarely enough, but that really matter to operating at this level of scale. And we have a really good track record thus far. Right? So we are, compared to human drivers, we've measured in controlled environments, so in controlling all the factors that we can control. We experienced 92% fewer crashes with injuries to pedestrians, 82% fewer crashes with injuries to cyclists, and 82% fewer crashes with injuries to motorcyclists. So that's as a sample of the kind of safety metrics. So that's getting to an order of magnitude difference to the average human driver. And in this environment, having this kind of superhuman performance is critical. And I really want to emphasize this, that we're not just chasing, how to drive correctly, how to be a good driver in the same way that you would sort of learn how to drive and try to pass your driving exam. We really have to be at a level of performance that is superior to what the average does. So the different problems that can be solved, that we need to solve, and that the foundation models can help us inform is the major questions: where am I? What's around me? What is going to happen next? And as a result, what should decomposing the problem of autonomous driving into its core components. Just to give you a sense of what it looks like in the real world, I'd just like to sort of frame things a little bit. That means being responsive to agents that are directing traffic. That means being responsive to changes in the geometry of the scenes, being able to do quick merges, being reactive to emergency vehicles on the way. I really like this one. This is a truck blocking the road, and we have to basically reason that the only way we can make progress is to back up and give enough space for the truck to pass and then to go back. A lot of humans would not really do that necessarily, and get stuck very easily. Another case is, this is the exit of a concert in San Francisco. Lots of people walking around. We want to be extremely safe around pedestrians, but we also want to get out of the way as quickly as possible to minimize the exposure, right? And so we want to be able to make progress in these scenarios. This is an example of being at night. A light is actually not working, and another driver just blows past through the windows. This is another example of bad driving. Anyways, just to give you a sense of flavor of all the things that we observe in sort of routine deployments and the things we have to be reactive to. So again, the long tail scenarios are really one of the things that drives a lot of the need for in-depth understanding of the world and in-depth semantics. And you'll see a theme throughout the talk is that deep semantics are really something that those large multimodal models can really bring to the table that are unique, because those are things that we don't observe in general in the data, in the autonomous driving data, or only very rarely. And learning from very few shots is not really a scalable way of figuring out how to address those issues. So you can simulate them, but you can also sort of learn from a more generally trained model on video images on the web, and just a model that also has very deep semantic understanding. Another way in which the kind of large language model revolution is impacting driving is that one way to think about the contracts that your car has with other agents on the road is as a conversation. And it's not a conversation in words, it's a conversation in motion. You basically negotiate, picture yourself at an intersection, you're trying to negotiate who's going first, and are you passing in front of another car, or is the car passing in front of you? This kind of subtle interaction and reaction to other agents is really a visual conversation with the other agents on the road. And so we can actually take that very literal and model the interaction as a conversation using what's called here motion tokens, and model the entire interaction as a sequence of tokens that take into account the entire agent scene, if you will, and is able to sort of reason about the interaction as a multi-agent sequence problem. And that's a very nice training, because that really sort of matches very closely the kind of autoregressive LLM frame of things. There's a lot of good research that has been applied to that training. There's a lot of interest in LLMs in general, and casting the AV problem into an LLM-like problem enables us to leverage all of the advances in that space. So this is an example of, just to illustrate what happens if you don't model interactions well, and if you don't have this joint prediction of things. You can have two agents that appear like the pedestrian and your car being predicted to collide. In practice, you will either yield to the pedestrian or the pedestrian will yield to you, and modeling this interaction is reduced. So once you have something that is framed as a LLM-like problem, you can take advantage of all the research that has been happening in particular in scaling those models to very large sizes. And indeed, we find that the same kind of scaling laws that have been observed in terms of the behavior of the system and the improvements you can get when you increase the amount of compute, when you increase the amount of data, when you increase the size of the models, and you optimize jointly for compute data and architecture size, you can get very predictable improvements in the performance of the model. Now, what changes is because we're not solving the same problem as the LLM, the actual constants that you have that describe that the scaling laws turn out to be very different. And that's a very interesting finding that the driving problem itself, while being able to be framed as an LLM problem, does not necessarily have the same scaling properties as the LLM problem. There's also scaling laws that we can use at inference time. When you're sampling multiple trajectories, you can make decisions about how many trajectories you will sample, and you can spend more or less time at inference time, and that also impacts how much compute you should be spending at training time, and different operating point have different results. I'm not going to go too much more into details into this. There is a fantastic and a lot more detailed talk coming up tomorrow by my colleague Vincent, this guy. And we now have a type report and archive that we can look at and see all the once you have an element that you've pre-trained and that you've scaled and you've done all your scaling law studies and you've trained on machine learning data, you can also take the playbook of post-training of the model and use it to do preference findings. And the general idea here is that if you're just imitating humans, you're probably also replicating human behavior, and your cost function may not match what the internal cost function of a human drug. You may, in general, for example, put a higher premium on safety guarantees than the average driver may want to, or you want to sort of put a different premium on comfort. Happier when they're at the wheel to drive in a less comfortable way when you're a passenger or in the car. All of those can be part of a purposeful design that you want to inject into the system. And one way to do this is to sort of address the alignment of your model with your desired loss in post-training. One of the approaches to this is to have human annotators actually rank responses and outputs of the model, very similar to what we would do with RLHF, but with a playbook for human annotation that has a stronger opinion about what is the right way to behave or not. And by feeding this back as a post-training signal into the model, you can basically reconcile the disparity between this simple next open prediction and the actual sort of loss function that you want to do. And that turns out to be very good. So this is an example of a simulation where you have a baseline model that is just indicative and that predicts that the car should just cut through pedestrians trajectory ignore essentially the warning that there is a pedestrian on the crosswalk. And when you do close training with preference line, you can nudge the model towards giving the pedestrian much wider areas. Same thing with braking too late and giving enough space to cars. Similar behaviors, and we're seeing a lot of very marked improvements in just the general behavior of the system when doing this kind of preference. Okay, so the other aspect, as I mentioned, is sort of leveraging semantics, and this is kind of an often shown semi-joke example, but just as a way to illustrate that if you want to be able to drive in a particular park in San Francisco, you may have a superhuman problem in your hands, and that using AI to solve it for you may actually be the but even not just for parking and understanding the rules of the roads, there are a lot of contextual scenarios in which having deep semantics is really an important factor in making the roads. If you just treat your cars as 3D boxes, and you see a 3D box in the middle of the road like this, you may not infer the full context of this is the car that's on its roof, and so it's an accident scene, and we should get away from there without interfering with the emergency personnel. And doing that kind of reasoning can really benefit from taking all in the contextual cues from the scene beyond just treating the scene as a composition of objects that is just as a parse of the environment. The semantics here at the scene level are really dominating. So within building models that do this kind of semantic understanding, and one example is this EMA model that we published last year. It's a very simple vision to future waypoint driving model. It's basically taking a Gemini backbone and then fine-tuning it on top using a combination of cameras for the vision, the context, the high-level command of where you want to go, and then supervising it with the future waypoints of where you want to go. Very simple conceptually, so not a lot of dependencies, but a lot of deep knowledge of the environment. You're just doing deep sort of complex representation of things. You can describe essentially all of this in a combination of images and text, and output text coding for the future waypoints. But it actually works really well, and surprisingly well compared to existing sort of state-of-the-art baselines. The EMA here is a model that is trained on publicly available data. We also train a model on internal data, just to show that basically all data does train. And so that's on the Waymo open motion data sets. We also have results on the machines data set. In general, this simple approach actually scales very well and provides very good results on all the metrics. So this is generally sort of the message that I wanted to give, is that there is a lot of things around foundation models that sort of open up new avenues to really think about the AD problem, and the fact that we can map a lot of the AD questions to problems that are very similar to a lot of the other problems that people have been studying in the LLM or the agency world, or in the multimodal large model world. The fact that we can reconcile a lot of what we do with the advances that are coming from that perspective really gives us new avenues to really improve our systems and leverage all these advances. This is more than an academic exercise. This is something that can really sort of improve a system that is deployed in the real world, and so this connection between sort of the academic setting of the problem and being able to really improve the lives of people is something that I'm really excited about. I want to show, because that's always a crowd pleaser, a few more examples of sort of the kind of things that we want to solve, assuming that I have connectivity. Maybe. Yes. So this is an example, more examples of like a child stepping in on in the car, a car trying to cross in. People appearing from nowhere and passing in front of the car. Runner trying to run through the lights. Again, these are things that, you know, if you saw it happen to, if it was something that happened to you on your commute to work, you would get kind of excited about or nervous about or really scared about, and you talk about them. For us, it's routine. It's something that we observe all the time. And so you really have to think about this long tail of problems, not as exceptions, but as the subject matter, the important problem that you have to really think about. And so. All right, so, and that's all I have. I wanted to leave ample time for questions. If you're interested in working on this problem, please join us, or please come chat with us at the booth. And I'll be around also to chat with people that are interested in hearing more. Thank you.
Hi, thanks for the very cool talk. So I'm sure with Emma, you're not planning to take an LLM and just like give it the gas and the pedals and the steering wheel and just have at it. So what's your thinking on the future of like integrating LLM style semantics with CPU critical latency constraint online?
So there's a few layers to that question. One of the things that is really nice about those sort of AI-centric models is that they're very creative. They really, when there's a problem in front of them, they provide you with very good plausible solutions and lots of options. So as a generic model, they're very good at providing proposals. You probably don't want to put those proposals directly in front of the gas pedal and the steering wheel. You probably want to have a layer that looks at those proposals and decides, maybe that's correct, maybe that's not. That's where a lot of the interesting logic can happen. It's a very common paradigm that we're seeing more and more in AI, that it's a lot easier to verify correctness than it is to generate a creative answer in the first place. Right, so putting all your parameters, your capacity into the creative generative AI and having a way of evaluating it based on the rules of the road, the measures of quality of behavior, measures of safety, is a general framing of how to think about integration of these models into a system. I think is very important. There is other considerations that are important. We rely a lot on simulation as a way to validate our system, because there are a lot of things that we never ever want to observe, but we want to make sure that if somehow we were to observe them for whatever reason, we would do the right thing in that scenario. So simulatability and simulatability scale is a large problem. So I'm excited about how these days a lot more generative models go down to pixel essentially and are able to do simulation of sensors, whether it's camera sensors or LiDAR sensors, and so we can close the loop and have simulations that eventually can sort of go directly from the input sensors all the way to the behaviors of the system. But that's also another thread that I think needs a lot of work and actually really benefit from a lot of attention from the technical world, because I think there's a lot of unsolved problems that still to be figured out in this.
Thanks.
You mentioned that the foundation models are really good kind of semantic knowledge, and especially that is coming from outside your data sets. I'm wondering if you could also comment on if you've evaluated them for nominal perception tasks like say video visualization. It seems like they might be poorer at that, but I'm curious to hear what results you might have got.
The current breed of foundation model is terrible at speech understanding. Terrible. And you understand why, right? A lot of the sort of traditional academic data sets that is in computer vision focus on semantics for so long that it's all the image generation that is, essentially it's like that, very poor sort of geometric understanding, and in particular, they may have geometric understanding in pixel space, but not very good in 3D space. And I think that's a gap that the computer vision community needs to really think about. The goal of computer vision is not to label pixels, it's really to label where things are at and the semantics of the scene and geometry, the geometry of the scene in the 3D world. That's starting to happen. I feel like in general, the sort of multimodal model providers are starting to see that this is actually a big gap in the performance of the models and starting to address it, because there's a lot of functional uses of large multimodal models that require very good geometric insights. But I think it's going to take a while. I don't think it's phenomenal gap. I think it's really just a gap. I don't think there's something really phenomenal about a large multimodal model that they can't really solve really. It may just be there might be a representation problem in some ways, but I think it's really a matter of focus.
Thank you.
Great presentation. My question is, all the videos that you showed, were you able to perform exceptionally well in existing pipeline, right? To avoid the entire crash scenarios, even better than humans, I would say. So what's the motivation of introducing the foundation models now? Like, what's the research you have? What is the case that the current pipeline fails in that the foundation model can help and alleviate those problems?
Yeah, I mean, we're doing well in the nominal driving. Scale brings new problems to the table all the time. So that's a very interesting thing about scaling, is that you drive 1,000,000 miles, you see the kind of thing that happens once in a million. You drive 10 million miles, you see the kind of things that happens 10 in a million. Right? So you always have new problems that surface that are more rare or more esoteric. And there is also a general issue around scaling in general, which is that we want to sort of generalize to more and more areas that you can run. Typical example for us today is we don't drive in snow. Snow is a very interesting new environment that has its own peculiarities. And generally, you cannot just take somebody who knows how to drive on a dry road and put them in a snowy environment and expect that from day one they're going to be very good drivers in that environment. It's practice, it's learning, and some interesting for the ability to something fun. So it's the same for our driver. We need to be able to do something. So there's a ton of sort of things like this that have to do with general relations with problems that we need to fix.
How you said we should focus on the long tail problems and not like exceptions. They should be like the mainstream problems. So
isn't the case that even for the multimodal VLMs or LLMs, we would have problem like dealing with those cases, because
It's fine.
again, data is
There.
limited and these models also don't perform as well. So, but you're using that to augment your own planning or projected planning, right? So how, I mean, again, Waymo has been doing amazing. So is there something more to it? Because I've also attended another talk, they also came up with the same finding saying that when it comes to long tail distribution, these big LLMs, VLMs are not performing as well.
So what's interesting is that what is in the long tail of our driving set may not be at all long tail for a model that is trained on web data. Right? So the rarely see cats, but there's lots of
He's the only one.
Right? So a little bit of a,
The first guy is the
getting the-
one next one. The second two guy are from the Duke University. Yeah, they are the winner of the track. Yeah.
country, for example.
And then we will add section that handling that certificate.
Or emergency vehicle. This probably a lot of examples of experience. And so what the definition of long tail is really sort of shifted by the fact that we can use other different and we leverage that to improve.
Okay, maybe one final question. Okay.
What about foundation models that are distributed among multiple vehicles, even like among vehicles from different companies, like vehicle communication or exchanging maybe crucial information, like the example you showed of this bicycle that appeared around the corner. Maybe if there was like another vehicle that was the bicycle was visible, there could have some warning for the vehicle.
Yeah, using third-party view from other cameras that are being put on other cars or on dash cams and things like this. It's really interesting sort of information. In general, one of the interesting things about those foundation models is that you can train them at scale and you can use them as supervision for the system that runs in the car, right? So you can really scale them up and not really necessarily think too much about the real-time constraints or the deployability or even which car you're deploying the system on. You can retarget them to be deployed in a way that is more efficient, that has the right properties on the car, and is more specific to the environment. So this possibility of sharing the model, the data, I think is a really interesting one and something that as a community we can definitely look at.
Thank you so much. Thanks. Yeah.
Sorry, I have one question.
Right.
Is it the same Waymo driver that is driving in all the cities? And just, I guess the broader question is, how much work goes into when you to a new city? Is there like city-specific behaviors that you can report into a driver?
I can't give you too many specifics about this. Our Waymo driver really is general, and the amount of work. Let's talk offline. There are a lot of things that are non-technical about deploying to new cities. It's a lot about sort of meeting the regulations that are all very distributed and local. It's about operationalizing, like we need to get cars in depots and things like this. So there's a lot of the work that about going into a new city that is largely invisible, has nothing to do with technical capabilities, but needs to happen if you want to be able to do.
Yeah, I meant more in the AV stack, like perception and localization.
In the AV stack, we generalize very well.
Awesome. Thank you so much. Next, we have the World Model Challenge by 1X.